Hello everyone, welcome to lecture 41. Today we will look at, so we finished module 2, which is about thermodynamics and looking at equilibrium properties. What is their origin, statistical mechanical origin, so microscopically what are these equilibrium properties, and we did some very minor preliminary case studies on how to design materials, right. So, what goes into this entire field of materials engineering to, let us say, or combination of materials, not just single material, to let us say enhance a certain property such as susceptibility or piezoelectric coefficient, or whatever it is, based on all the knowledge that we had. Okay. And in the first part of the course we actually looked at symmetries, and we said symmetry takes you to a certain extent. Symmetry allows you to say if a certain property exists, if certain property has a tensor, a certain tensorial element of a property tensor exists or does not exist, but it does not give you the magnitude of it, right. So, for you to be able to get the magnitude of it, you have to look at the origin of these properties, and some of these properties are what are called equilibrium properties, and that is the second module, right. So, we finished it in the last class. Today we are going to look at what are called dissipative properties, and these dissipative properties have of course they dissipate something, they dissipate energy clearly, that is why they are called dissipative properties, whereas equilibrium properties that we studied in module 2, they do not dissipate energy, they store energy, right. So, we were looking at capacitance or susceptibility or dielectric constant. The by virtue of a material having its dielectric constant, the material is storing energy, electrical energy, that is, right. By virtue of a material having a Young's modulus, or if a spring mass system is operating in its linear regime, it is storing the spring energy, right. So, by stretching the spring, I am storing mechanical energy in the form of stretched bonds, or so the stretch of the spring, and so on and so forth. So, these are energy storing mechanisms that we have seen. Now, we are going to look at energy dissipating mechanisms, right. So, energy dissipative properties, right. And so as you all know, right. So, if I have a resistor, right. So, if I go for simple Ohm's law, V equal to IR, right. So, this is a resistor dissipates energy. So, by virtue of V equal to IR, what I have is, as I keep sending current through this resistor R, I end up creating this Joule heat, right. So, I dissipate energy in the form of what is called Joule heating, right. So, what is the power that I dissipate? It is either given as V square I square R or V I, right. So, to be more precise, the power dissipated is given as V I, right. And the underlying property of the V I power dissipated is the resistance of the resistor, and my resistor here is a material, and so we will look at such properties that are going to dissipate. So, this is a dissipative energy, right. So, this is dissipation of electrical energy, and by contrast, storing of electrical energy happens in a capacitor, right. So, storing of electrical energy happens in a capacitor, right. Something to always keep in mind, right. So, a capacitor stores energy, a resistor dissipates energy, right. So, we will use these analogies to actually discuss more generally how properties are going to be dissipated. Okay. Okay, so now all right, so where else have we seen dissipation, right. So, I have a spring mass system, let us go back to our spring mass system, right. I have a spring mass system where so which goes so if I apply a force on the spring mass system, or if I pull the spring mass system, there is a restoring force that goes as minus kx, that is okay, right. But there is also a dissipative force which goes as minus Cv. Okay. So, this is what is called a damped spring mass system. Okay. Now, this is F equal to ma, so or mx double dot plus kx, right, plus Cv, V is the velocity with which the spring is moving, right. So, so at any point the spring can be moving. So, the velocity with which the spring is moving, that is x dot, that is equal to 0. This is the equation of a damped spring mass, right. And the damping here, right. So, x dot is the velocity, right, which actually tells me about something moving, right. So, so this term C x dot tells me the friction force acting on the spring mass system, and that friction force is responsible for damping the spring mass. Right. If there is no friction, right. So, if there is no friction here, then if I stretch the spring and release it, the spring will keep on oscillating forever, right. So, about its equilibrium position, but because of the friction there is a damping, and then eventually the spring stops to move, and and that's what damping provides, right. So, all the fluctuations that are provided in some sort, right. So, through these equilibrium properties are sort of damped off by these damping properties or non-equilibrium properties. Now, if we look at this Cx dot term, right, F equal to or minus Cx dot term, right. So, what is the property that I am interested in here? So, I am actually looking at a force which is the friction force, right, and I am actually looking at the flux or some sort of motion, right, motion of the spring mass. In other words, the you can see it in whichever way, but here the so let me write it this way, 1 by c of f equal to minus 1 by c of f is equal to x dot, right. So, in other words, if I have flux as the effect, right, and force as the cause, I am related to force and flux through a friction coefficient, right. So, the property of interest is my friction coefficient of friction, right. Now, it is or so it is these coefficients of friction that we are going to look at, right. So, we are actually going to look at friction forces and coefficients, friction forces as dissipative forces, and coefficient of friction right as the property that allows the system to dissipate. Now, how do I know the system is dissipating, right? So, if I apply a force, this is I apply a force, because of dissipation there is a flux, right. So, something keeps changing, so there is some sort of a motion, right. So, if I push you, you go back and you fall down, right. So, that sort of a thing. So, so there is a force and then there should be a flux, something should move, right. And then so I am going to say that I am going to actually prove that if I apply voltage or if I apply an electric field, current moves, electrons move or charge carriers move. So, there is a flux of charge carriers. So, the force is electric field here and the flux is the motion of charge carriers, and there is a force and there is a flux, and hence there is dissipation, right. If I stretch a material, right. So, if I apply constant force on the material, right. So, I am doing some sort of a tensile testing experiment where I apply a constant force on the material, the force is constant and the material will start stretching and stretching and stretching, right. So, this spring is just moving and stretching and stretching and stretching. So, there is some sort of a flux of the material, right. So, the material, I mean, the length of the material keeps stretching and stretching. So, there is a flux in strain, if you may think of it that way, right, and that is nothing but my plastic deformation in metals, right. So, it is called creep, right. So, creep in metals means I apply a constant stress, right. So, I apply a constant stress or constant force in some sense, and because of this constant force the material has some material keeps expanding. Or in other words there is some x dot, right. So, I create some sort of a strain rate in the material, right. So, by applying force, if I am just stretching the material forever and ever without really changing the magnitude of the force, that phenomenon in metallurgical engineering is called, or in mechanics is called creep, right. So, the material is creeping. Now, creep is what is called plastic deformation. Not elastic deformation, it does not store the mechanical energy, rather no storage of mechanical energy, it is not a Hookean spring anymore. Rather the energy is dissipated. Okay. Because you cannot really retrieve back, so once so if I have a stress strain so here is capital X, here is small x, stress strain diagram. So, initially if I am doing some sort of a tensile testing experiment and I apply constant stress. So, this is what is called a tensile testing experiment, right. So, initially I am in this Hookean regime, right. So, where stress is proportional to strain. Then I enter this plastic deformation region, and here I cannot, if I remove the strain after a while, right. So, I cannot really bring back, and then so if I remove the strain, so I am straining the material. So, I apply this much of strain and then I remove the strain. So, even at 0 strain I still have some stress, the material is still stressed, right. So, I cannot get back to the 0 region, right, or so even at, if I want to go back to 0 strain, I need to apply some more sort of compressive stress. So, I need to generate some compressive stress in the material, so that I go back to 0 stress, right. So, all this, right, so is the energy which is dissipated in some sense. Okay. So, we are actually going to look at that. So this is plastic deformation, but so if I just apply constant stress, right. So, if I apply constant stress is constant, but the material just keeps straining, right. So, with time, right. So, the material just keeps straining, or if I plot x versus t, the material strain just keeps increasing with x versus t. This behavior is called creep, and even in creep I have energy which is dissipated. All this energy under the x curve is energy that is dissipated. Okay. So, that is the mechanical problem. The electronic problem is if I have if I apply force on charge carriers, which is field in some sense, right. So, which is actually electric field, which is voltage per unit distance, then I generate a flux of charge carriers, which is nothing which we call current, right. So, I apply electric field, I generate current. What relates current with with flux is my quantity sigma, right. So, this is like the force, this is the flux, and my sigma, which is this is Ohm's law. Sigma is the dissipation, or sigma is the property that tells me about dissipation of electrical energy. Sigma tells me, sigma is the conductivity, right. So, conductivity is a dissipative property, dissipation of electrical energy. Okay. So, now let us actually prove that so if I have a force and I have a flux, a force that creates flux of something, right. So if I have for example, if I have a gradient of concentration, right, so that is like my force, right. So I have a gradient of concentration. I'll actually show to you that gradient of concentration, or what is called gradient of chemical potential, is actually can be considered as chemical force, right. So this is chemical force, right, which means, so I have, let us say, in this box I have less number of molecules here and more number of molecules here. So this is denser, this is rarer, right. So then what happens, all these denser molecules will start flowing, right. So let us just assume this is in gaseous phase, will start flowing towards the rarer this thing, right. So this is nothing but this is diffusion, right. So I have minus di, so gradient of concentration is nothing but my flux of I, right. So this is the diffusion equation. So my diffusivity di is again a dissipative property, or more appropriately, rather than diffusivity, I call it the mobility, right. So how do I represent mobility? I am just going to represent it as Mi, right. So now mobility is a dissipative property, and then diffusivity and mobility are related. We are going to go into details of that later, but so mobility of my atoms here. So atoms have some mobility, which means they are able to move around, right. They create a flux of atoms, this is flux, this is the chemical force. So there is force relating to flux, and so diffusion, the process of diffusion itself is dissipative in nature. It dissipates the chemical energy, right. So so diffusion dissipates the chemical energy. Okay, then so what about thermal conductivity? So we have delta T, right. So if I have a gradient in temperature, that is like my thermal force in some sense, right. So gradient in temperature, I am actually going to show that this is analogous to a thermal force. So minus K, which is the thermal conductivity, gives me the flux of heat, right. So this is the thermal force that drives my in some sense, so you can think of this as something that is driving the flow of heat as an energy, right. So we do not associate heat flow with flow of physical particles, but this is flow of energy, right. But this is the force, or this is related to the thermal force, and so the property that I have here is thermal conductivity. It creates a flux of heat, right, and the flux and force are related through a property which is dissipative in nature. So this is dissipates the heat energy. Okay. All right. So fundamentally we then come to so how are these things dissipation? What is dissipation really, right? So dissipation is okay. So I am spending energy that is irretrievable, that is dissipation. Right. So thermodynamically speaking, I am speaking about some sort of an irreversible process, right. I cannot really go from state A to state B without losing out on anything, right. So and it turns out what I gain in dissipation, the other way of looking at dissipation is I am actually generating entropy, right. So I have this S dot term, so I generate entropy during dissipation. Okay. Now what does it mean that I am generating entropy, right. So if I have S versus T, right. So for any system, right. So any system would eventually want to go to equilibrium, or system meaning system plus surroundings, right, plus surroundings would eventually want to go to equilibrium. So if I plot entropy as a function of time, entropy increases and eventually it sort of settles down, right. Now we are so if I need some S dot, right. So if I need some generation of entropy, I am not looking at equilibrium systems, this is the equilibrium system, right. But here until it reaches equilibrium, all this is non-equilibrium, right. In non-equilibrium systems proceed towards maximizing entropy, and once the entropy is maximized and it stabilizes, that is where the system becomes, or system meaning by here I loosely use the word system, but it is system plus surroundings, right. So, system plus surroundings become so they tend towards equilibrium. This is exactly what is meant by so going towards equilibrium. So, it goes towards equilibrium by increasing S as a function of time. Now, time comes into picture, right. So, I need to generate, or so how can I just increase entropy? I have to generate entropy from somewhere, right. So, this is the thermodynamic picture again, non-equilibrium thermodynamics this is called, not equilibrium thermodynamics, right. So, so I should keep generating entropy, so I need to generate entropy, and it turns out that whenever I generate entropy, right, so S dot is sufficient to say that my system is dissipating. Or dissipating energy, right. So, energy is being lost, right. Now, how can I lose energy, right. So, let us ask that question next. How can a system lose energy? Whatever be the form of energy, the way you lose energy is to heat, right. So, system loses energy by generating heat. Right. So, again let us go back to the example of a resistor. I am applying a force, right. So, which is electric field, and I am sending in current through the resistor, right. So, the system is actually losing heat, or sorry, the system is actually generating heat, it is joule heating, the resistor is joule heating at a rate which is equal to V I, right. So, this is the power that is dissipated, V I is the power that is dissipated. Okay. So, now we are going to now show you that this V I power dissipated is nothing but this is heat, right. So, this is joule heating, that is what we keep saying all the time. So, now I am going to derive that this is indeed nothing but heat, right. Now, if I am going to, power is what? Power is actually energy per unit time, right. So, now what is, if I am looking at the heat energy, right, in a system, right. So, thermodynamically I am just going to look at it as T s, right, but the power, right. So, which is energy per unit time is nothing but T s dot, right. So, S dot, where S dot is d s by or dou s by dou t, which is the generation, right, generation of entropy, not just some exchange of entropy between one part of the system and another part of system, but I have to generate entropy, right. So, in the entire universe, right. So, that is what the power dissipation means, right. So, now in what follows quite mathematically, we are actually going to show that this T s dot is nothing but so it will be electrically, I can think of this as V I term, right. So, again this is the flux, sorry, this is the force, this is the flux, right. Electrically I can think of this as F, which is the force applied on a spring times x dot, which is the extension of the spring, right. So, all these are actually power dissipated, and all this I am going to show you very soon that are going to be related to T s dot, where s dot is nothing but the generation of entropy, right. So, if I generate entropy, that is equivalent to losing my energy to heat, right. So, heat is some sort of an incoherent form of energy, this we have studied in thermodynamics, right. If you are heating something, that means you are irretrievable, I mean, so okay, there is you can do all these thermodynamic cycles and try to retrieve some of the heat back into useful work, but then you have to actually construct these cycles, and even then so the efficiency of retrieving heat is only 70 whatever Carnot efficiency is, right. So you cannot extract out all heat into work, some of it should go, right. So it is just dissipated, right. So my things just heat up, they vibrate, right. So all these bonds just vibrate, and in vibration I'm just letting the energy go, right. So this is dissipative in nature, heat is dissipate, I mean so by converting, so by here for example in Vi, right. So I am converting electrical energy into heat, which is again, so the electrical energy I supply to electrons, right. So what is happening here, so I apply, this is my resistor, it's let us say a wire of something, I apply voltage to the wire, then so this is actually carrying some sort of charge carriers, right. Electrons are moving in sorry, not electrons, actually positively charged particles are moving in this direction, or electrons, if you are thinking about electrons are moving in the opposite direction, right. These electrons start hitting the ion cores, there is an interaction, an electron phonon interaction or electron lattice interaction, and so just by colliding with these ion cores, these electrons give out their energy, right. So they are energized by the electric field that I am applying. Electrons are energized by the battery, right, and they give away their energy to lattice vibrations, and this is what is nothing I mean, so this results in Joule heating, right, with the power dissipated being Vi, and this is irretrievable, right. So once the lattice starts vibrating, right, so I have an I cannot really, I mean, unless I use very smart strategies, right, so I cannot really retrieve back what is just heated and lost, right. So this is lost energy. Can we control it? To a certain extent, but can we control it completely? No, there are always losses, right. So you have to live with it, right. So you can try to minimize them, but they always exist, okay. So so the properties, and then every material has a property that tells me how much am I going to lose, right. If my resistance is huge, right, or if my conductivity is very small, then I am not possibly losing so much energy. I cannot put in so much current into this material that I am losing energy. Then it behaves like a capacitor, right. So where it stores energy, right. But if I have a metallic wire, right, so where the resistance is small enough, conductivity is large enough, then I am just so I am just heating up the so by sending in current into platinum, I am just heating up platinum, and so I am dissipating all my energy, okay. So so this dissipation is some sort of an irretrievable form of power, right. So we look at dissipation in terms of power dissipated, and power dissipated is just nothing but Ts dot, okay. So so Ts is the heat energy, and Ts dot is the power that is dissipated, okay. So now we are actually going to look at over the next few minutes what is this, I mean, so how is Vi equivalent to getting entropy or producing entropy, right. So just to close the loop, right. So entropy production is the same as power dissipation, okay. So let us go back to basics, and then let us see if Vi is actually producing some sort of an entropy, okay. So so let us look at it this way. So let us again start with the first law of thermodynamics, where du is del q plus del w, right, so in a closed system. The convention del q or del w means work done on the system is positive. And the convention del q also means work heat produced on the heat given to the system is positive, right. So these are the conventions. Yeah, so you give heat to the system, you also do work on the system. So this heat plus work gives you the total increase in internal energy. That is how we formulate, or that is how we understand the first law. Okay. So, this thing we have done earlier. Then du is actually I am going to write it as del q, so minus so if I apply, let us say an electric field, right. So, I apply an electric field on the system, then I generate polarization. So, it is minus EdP, right. Then I apply stress, right. So, and I generate strain, right. So, it is capital X dx, right, and so on and so forth, right. So, so in general the work done on the system is electrical work, mechanical work, right. So, let us confine ourselves to electrical and mechanical, but there can also be chemical work. Chemical work is just so I have a chemical potential, and the chemical potential changes the concentration mu dN or something like that, right. So, again I have to do a 1 by V here, but anyway, so these are the sort of things that I have. Okay. Now, you may want to actually be a bit careful about the units here. So, when I say du, I am actually looking at the total internal energy divided by volume. So, this is some volume normalized internal energy. Okay. So, when I say del q, that is also del capital Q by V, right. So, this is also volume normalized heat. When I say EdP or the electrical energy, right. So, d let me just call it as okay. So, EdP E dot dP, right. So, that is nothing but so I apply so this is V dq, V being the voltage, and that is also normalized by volume, right. So, okay, so I have to be careful. So, I am going to write this V for voltage and this V for volume, right. So, where V is the voltage applied, right, and so V by D is nothing but E, and dq by A is nothing but P, right. So, or dP, and so so when I do V dq by total volume, then I get E dP. So, these are one and the same in some sense. Okay. So, this is I am doing some sort of volume normalization. Okay. Sorry, volume yeah. So, I divide with respect to the volume. Okay. So, when I do these sort of calculations, then if I do x d small x, right. So, then I am actually looking at the force times displacement, right. So, displacement, so this is we used d delta to represent displacement, right. So, this is displacement, and that is also volume normalized. So, force by area gives me the stress, and d delta by just L, that gives me the strain, right. So, as a result, these two are one and the same, it is just volume normalized, right. So, in understanding what force is and what flux is, so this sort of, let us keep this at the back of our minds. Okay. Okay. So, in general, the delta W, right. So, delta W is given as so this is the work done on the system. Work done on the system is so if I am applying an electric field, and generating a polarization, or if I am so if polarization, if I am charging the system would generate an electric field which is in the opposite direction. So, minus E dot dP, right. So, the way to interpret this is, if I am charging the system, if I am polarizing the system, right. So, that is my dP, that is my cause. The effect is an electric field, but the electric field will be in the opposite direction, right. So, so I'll create an electric, this is like I have or minus f dx, right. So, if I am straining the system dx, I am generating a stress which is a restoring force, right. So, this is the residual stress or restoring force, right. So, this is what is called restoring field, or in other words this is what is called depolarizing field, but okay. So, those are semantics, we will come back to that later. Okay. So, now minus and so on and so forth. Then if I actually look at what delta W is, I can have a magnetic field, right, and I can create a magnetization, it can also be that, right. So, I can have several such inputs, several such stimuli, and I can generate the output, right. So, I can generate the effect. Okay. So, delta W in general I am just going to write it as minus psi j d whatever this character is, I always keep forgetting what this character is, sigma of that, right. So, where j 1 j so how many ever inputs I have, right. So, this can be polarization, this can be strain, this can be magnetic field, right. So, epsilon j can be polarization 1, polarization in second direction, polarization in third direction, right. So, or it can be strain, right. So, whatever xij tensor, sorry, xkl tensor, let us say, or it can be magnetic it can be magnetization again M1, M2, M3, or so and so on and so forth, right. So, any sort of all these are actually work done, right. So, the electrical work, the mechanical work, the magnetic work, all these come under this general formula, right, for delta W. Okay. So, now we are going to rewrite our equation as so let us say du, everything in small, delta q minus sigma j psi j d, I think let me just call it I think xi, or I don't recall what this is called in Greek, but okay. So, let me just call it for the time being, I will just call it dej. Okay. So, where again E is nothing but E is some extensive quantity, or E is derived from an extensive quantity. This symbol, this Greek symbol is derived from an extensive quantity. And psi j is the intensive quantity such as voltage, temperature, etc. Okay. Okay. Now, instead of del q, right. So, if I am just going to write this as T ds, right, and small s minus sigma j psi j epsilon j, right. So, I mean I am close enough to equilibrium that I should be able to write something on these lines. Now, so let us just look at, so we want to look at what T s dot is, right. So, T ds in that sense is nothing but du plus sigma j psi j d epsilon or dej. Okay. So, this is the equation that I will start with, right. Okay. So, sorry, I just made a sign mistake. So, okay, so this is the work done on the system, right. So, if I am applying electric field on the system, the work that I am doing on the system is going to be positive, right. So, that is my simple signature sign mistake. So, there will be a plus here, there will be a plus here. So, there will be there is going to be a minus here. Okay. So, let us follow the signs quite carefully. Okay. Okay. So, now I am going to so go towards what is dou s by dou t, right. So, what is the change in entropy as a function of time? This is the quantity that I want to actually understand, right. So, I want to look at what is entropy generation, right. So, now that will be 1 by t dou u by dou t, that is all right. Okay. So, minus 1 by t sigma j psi j dou this E by dou t. Okay. So, I have brought in some sort of flux terms, right. So, I am looking at the flux of entropy dou S by dou T, I am looking at the flux of internal energy, and I am looking at the flux of some sort of an extensive quantity. This can be flux of polarization, this can be flux of strain, this can be flux of atoms moving around, right. So, polarization meaning flux of charge, right. So, this can be flux of charge, this can be flux of atoms, anything, any flux, right. So, I just bring it down to this sort of an equation. All right. Now let us look at so if I have let us look at what is called conservation equation. Which I am sure some of you may have seen in other courses, right. So, conservation equation is going to be important here. Here so let us say what is, I have a volume of material, very small volume of material, right, or I have a volume, right. So, this is I have a road, right. So, on this road I marked certain position, right, and so that position has some area or width or whatever volume, and there are autos that come in and autos that go out. Okay. Now, let us define what is called the concentration of autos, right. So, concentration of autos C I is the total number of autos in the volume of, in this volume that I have selected, divided by volume. Okay. So, that is the concentration, it is simple definition. Okay. Now, what is the flux of autos? J q, right, sorry, J autos. Now, flux means it is number of autos that are coming out, no actually flux through this, right. So, number of autos that are going in minus number of autos that are coming out okay, divided by the area, right, divided by the time. Right. So, so this is the number of particles per unit time per unit area, right. So, that is so number of autos that are coming in minus number of autos that are going out. So what is the flux that is coming in, what is the flux that is going out, let us put it that way, right. So, instead of defining flux of autos coming in is what, let us flux of autos coming in, right. So, that is J q in is the number of autos that are coming in through this phase, right. So, on this phase, right. So, that is how they can come in. So, number of autos in divided by the area of that phase, right, times area of 1, let us call it 1, right. So, and this phase I am going to call it 2, the green phase is 2, divided by the time, right. So, number per time, that is flux. Okay. Then flux of autos going out of my volume, right. So, that will be equal to J q out, that is number of autos that are going out through phase 2. So, I am going to write this in green, right. So, number of autos that are going out through out, and this is out, right. So, this is coming in, this is going out, divided by again A times T. This time A is that of A2, this is A1, but A1 so the way we defined it, A1 equal to A2. So, here I am just going to write that A1 equal to A2. Okay. Now, what is so if I am just saying that so all the autos that go in should come out, right. So, all the autos that go in should come out of the region of interest, right, and that is nothing, that is called conservation of autos, right. It is so none of these autos can disappear if all autos that are going in comes out in a regular scenario where traffic is flowing, let us say traffic is flowing nicely, all autos that go in come out, right. So, if all autos that go in are coming out at the same rate, so that traffic is flowing sort of freely and there are no traffic jams and other things. So, then we have conservation of autos and so if there are conservation of autos, then we say so the number of autos that are changing, right. So, dou Ni by dou T per unit volume, right. So, I am going to look at this term, that is dou Ci by dou T. Okay. So, these are the number of autos that are changing per time in this unit volume. Right. So, the thing is all autos that go in should come out, they may come out at different times and other things, that is okay, but all autos that go in should come out. Okay. So, now dou Ci by dou T, right, is equal to the flux of autos that is going in minus the flux of autos that is coming out, right. Okay. Now, flux is just number of autos per this unit length, right. So, per the unit length is some L. Okay. So, it should be so I mean you can actually see that. So, that is number of autos that are so you can easily write this as number of autos that are going in minus number of autos that are coming out, right, per unit volume per unit time, right. So, that is this expression and that is nothing but the flux of autos that is going in minus the flux of autos that is coming out divided by flux has number by area time divided by L, right. So, in some sense that gives you the gradient of the auto flux, right. So, this is gradient of the auto flux. Okay. So, we have this equation where dCi by dt equal to minus the gradient of flux of autos tells me that there is conservation of autos on the road, right. Now, if autos are not conserved, that is autos go in, right. So, this is my region of interest, right. So, this is some black box, right. So, this is let me color it in black so that I know that this is a black box, right. So, this is a black box, right. Now, if it turns out that in this black box inside of this black box I have some auto creation factory, or this is like my Bermuda triangle where autos that go in just disappear, right. So, or auto destruction factory. I do not know what is inside this region, autos go in and autos are destroyed, or autos go in and autos are created, right. Then so the equation so I have minus dou Ci by dou T equal to minus flux of autos, right. So, gradient of the flux of autos. Now, plus there is some sort of what is called generation of autos, right. If I am generating autos or destroying autos, right. So, I have to add that also, right. So, this is number of autos that go in come out, right. So, this is the conservation law, but if I have new autos that are generating or destroying from this region of interest, I have to put in the generation term or the destruction term. So, I am just going to put Ci dot, right, where I am this is the generation or destruction of autos. Okay. So, now in the next class what I am going to do is I am going to use this conservation law, right. So, if you go back and see right. So, I have this equation where I have change in entropy with respect to time, I have change in internal energy with respect to time, I have change in some sort of a conservative work with respect to time, right. So, I have change in work with respect to time, right. I am going to look at all these things from the ambit of conservation laws. I am going to say u is conserved. The number of particles, or so the electrical energy or the the charge particles that are conserved, right. So, or the number of so I use conservation laws to look at this, okay. So, in terms of electrical energy, right. So, the charge number of charged particles will be conserved, or the number of atoms that are moving in a material will be conserved, right. So, these are actually conserved quantities. Whereas, if I am looking at entropy, entropy is not a conserved quantity. I can always generate entropy, that is what second law of thermodynamics tells me, and it wants you to keep on generating entropy, right. So, I go to this equilibrium state by generating entropy, right. So, this is not a conserved quantity, right. So, I use this expression for conserved and non-conserved quantities, right. So, and then I will try to mathematically go to this state. Eventually my aim is to show that Ts dot is exactly the same as Vi, is exactly the same as Fx, and so on, Fx dot, and so on and so forth, okay. So, I'm going to do this in the next class, right. So, I'm going to look at the power dissipated by through this mathematical framework, okay. So, let us meet again in the next class.